I introduced the concept of springs and Hooke's law and the spring constant. This video will be a little shorter and we'll get into talking about the elastic energy or elastic potential energy that springs and elastics and other devices that bounce back to their shape will have. When we're dealing with elastic energy, now, first of all, some people will use energy as a symbol of E with a subcase E to mean elastic, just like they would say energy potential or energy kinetic. Let me just write that in there. Elastic or potential or kinetic. Other times you'll see the symbols just elastic energy, potential energy, or kinetic energy. Different representations by different teachers or different books or different websites. So, very simply, the formula for elastic energy is 1/2 times the k value times x squared. We'll do a few examples using this equation. How much energy, okay, so energy, that's going to be elastic energy, is used to pull a spring 15 centimeters. So that's our x is 15 centimeters. And the spring constant K is 48 newtons per meter. Once again, we have to recognize that this needs to be in meters. So make sure you convert it into meters every time. Our formula, our energy, I'll write it this way this time, equals 1/2 kx squared. So it's going to be 1/2 multiplied by 48 newtons per meter multiplied by 0.15 meters squared. So 0.15 squared times 48 divided by 2. This example has 0.54 joules of energy. We are going to look at the units here just to be sure that it is joules, but we're expecting joules because we're talking about energy. So if we look at the units, we have, first of all, the 1/2 has no units. The K value is newtons divided by meters. And the distance, the x, is meters squared. So what's going to happen here? So basically we have newtons times meters divided by meters. And one of these meters divided by meters is 1. So we end up with newtons times meters, which is a joule. Here's another example for us. This time the spring is being squished. Once again, the x value is 4.8 centimeters. Be very careful. That will be 0.048 meters. The energy is 18 joules. And we want to know the spring constant. Okay, so I'll switch colors there. The elastic energy is kx squared divided by 2. I like to put a half in front. So a little bit of algebra here. 2 times the energy is kx squared. And we want to know the k value. So the k value is 2 times the energy divided by x squared. Okay, so in this example, K equals 2 times 18 joules divided by 0.048 meters. Oh, we're going to get a big answer. Well, that was 0.48 squared. Be careful we get that. So that's 2 times 18, that's 36 divided by 0.048 squared. This one has a really big K value, 15,625 newtons per meter. I'm going to just double check my units. Let's see, here I got joules, and joules is a Newton meter divided by meters squared. Once again, the meter on top will cancel out one of the meters on bottom and give me newtons over meters, which is what I have. Another example. Once again, we have 2.5 joules. I'm saying joules of work. This is energy. Energy is doing the work. So this is our energy. And it's being done on a spring. We have a constant. We have the K value, 15 newtons per meter. I want to know the force. That's a little bit different. We know that our E is 1/2 kx squared. We also know that the force is the K times the x. So what we could do is we could find our x value and then the force. There is a shortcut, but let's do the long way to start. I know some of you guys like the hard long way. I like to do the algebra first, but okay, here we go. So we're going to see that the x, I'm going to just go quickly to it. If you need help with the algebra, go back to the last question, but it's going to be 2 times the E divided by the K. That's going to give me the x value. Okay, so x is the square root of 2 times 2.5 joules divided by 15 newtons per meter. So 2.5 times 2, that's 5. And 5 divided by 15, wow, this is a third. That's going to be, wow, for those that are good at I can do that. That's going to be the square root of a third. Okay. Anyway, let's get that in decimals for those that don't like your radicals. So it's 1 divided by 3. So this is going to give us an x of 0.57735, just over half a meter. All right, then what we can do is we can take that and put it into our other equation that the force is K times x. And from here, I can see that the K, once again, we had the K way back here. K was 15. So 15 newtons per meter times 0.57735 meters. And all that, and I have an answer of 8.66 newtons of force. Now, that's in the positive direction, whatever that is, the positive direction. Now, I'm going to do this where I'm going to combine my equations. So I'm going to do this a little differently. Once again, we knew that the energy is 1/2 the kx squared, and we know that the force is the, where did we go with that? The force is K times x. So can we combine all this into one big equation? Let's see. We know that, where am I going to go? I want to know the force. So the force is K, and we know the K times X. And what was X? If we go back here, X is the square root of 2 times the energy divided by K. All right, let's see. So the F, I could put the K back inside that root. That would be like saying 2 times the energy times K squared over K. And now I can see that one of these K's will cross out with the other. That's in the denominator. So I have a new formula that the force is the square root of 2 times the energy times the K value. Might be a little bit less work to get the answer in the future. Just to see if it does the same thing, let's see, this is going to be the square root of 2 times 2.5, because that was our energy, and K was 15. So let's see, that's 2 times 2.5 is 5. 5 times 15, 5 times 15 is 75. And the square root of 75. So this is the square root of 75. Wow, you know what I'd rather do is I would rather say that's 5 times the square root of 3. But for those that don't like your radicals, 8.66 newtons. I found that a little easier. Oh, look at that. Same answer.